Thank you. Hi everyone, I'm Ira. You probably see me around volunteering this week. I'm supervised by Peter, who some of you might have met at dinner yesterday. I'm Rich Kurzweil, and I'm also part of the AI for AR CDT based here in Cambridge. So the kind of big picture is atmospheric zonal jets. Why do we care about them? Well, they're a massive driver of weather, especially here in Europe. And the kind of features within jets that I couldn't get the video to work, so this is a PDF. But what you would see is you'd see the kind of wandering dynamics of the jets in the atmosphere. We might see two jets merging together, and we might see the nucleation of other jets. And these are the kind of dynamics that we're interested in and going to try and model. Why are we looking to replace this with machine learning or capture the dynamics using machine learning? Well, the jets themselves are kind of characterized. They are generated and sustained by turbulent eddies. And on this sort of spatial scale plot, the ECMWF IMF forecast currently runs at a 10 kilometer resolution. And at that resolution, all the turbulence is having to be parameterized. And that parameterization is one of the slower parts of their forecast system. So we're looking at ways to speed that up. And the other important way to parameterize this is to use what's known as stochastic parameterization. So because we're looking at both a chaotic model and also there's a number of uncertainties within our parameterization schemes, we can't rely on a single deterministic parameterization. So we have to parameterize in a stochastic manner and run ensembles to be able to capture the uncertainty associated with the model, with these dynamics. And because I don't have the kind of compute that NVIDIA, that Jack was talking about with NVIDIA with 40 teraflops or however many GPUs they're using to emulate these climate models, we're going to use a very idealized model. And that way we can also look at the underlying dynamics as well. So we're going to look at what's known as a quasi-geostrophic, barotropic, stochastically forced flow on a beta plane. And we start with the shallow water equations. We parameterize the turbulence with some stochastic forcing here. And we get this equation. Don't worry too much, just that it's forced stochastically. And then often in parameterization schemes, we want some, first I'll go, and then these are the kind of fields that we get. This is the vorticity field, this is the zonal velocity field, and this white line is the zonal average, which will become important in a second. And when we're trying to create some sort of parameterization, we need some sort of separation of scales to kind of model the impact of the small scales onto the larger scales. So we use, in turbulence, what's often used is kind of called a Reynolds decomposition, where we decompose our mean flow, which is U bar, and our fluctuation fields. And then appropriately, we can write down some equation of motion for our zonal mean flow, which was that white line you saw before, and then the associated fluctuation fields. And notice that the stochastic forcing now, because of the way that we prescribe it, only appears in the fluctuation fields as opposed to the mean fields. So we have this coupled equation where we force the fluctuations. They have an impact on the mean flow. The mean flow then impacts how we model the fluctuations again. And then what we can do is we can put this in a sort of compact form with some sort of operator that models the fluctuation fields and get sort of an equation of motion just for the mean flow here. And then if we plot the mean flow as a latitude time plot, and because we're dealing with a stochastic system here, we have to show ensembles to show the nature of variation in our system. So after this initial conditions up to this dotted line are all identical, and then beyond this dotted line are different realizations of the noise. There's no perturbation. We just have different initial condition, different realizations of the noise. And we can see this very simple model still gives us the kind of nucleation, merging, and wandering dynamics that we saw before. So even this simple model can capture the complex dynamics that we're interested in. And now we have the question of, can we generate a data set from a single realization of this forcing, as we would have in the atmosphere? We only have one realization to go by. Can we use machine learning to learn essentially the dynamics of U and implicitly parameterizing that operator G? And one field and one way that ForecastNet in particular models their system that Jack was talking about earlier is they use what's known as called operator learning. But that assumes that the system is Markovian, i.e. you only need one instance of previous time history to be able to predict the next. But that integral up there means that we don't have a Markovian system anymore. So we have to take into account temporal correlations. So we need some sort of alternative to neural ODEs or these kind of methods. So what we're going to use is we're going to use a transformer, but we're going to do it slightly differently to how, as I said, neural ForecastNet, ClimateX, these other big weather emulation models have used, which they use a kind of a version of the vision transformer. So they ignore kind of temporal correlations and they look at spatial correlations only. But we know that the temporal correlations are very important. So to deal with the kind of complexity that comes with transformers, we're going to use an encoder-decoder structure to reduce our spatial information independently of time. So we give a number of time histories here, reduce that into a latent space, and then the kind of the stochastic part of our stochastic latent transformer is that we add in a noise vector here, and the transformer takes in our time histories and this noise to try and create an output. In trying to define a loss function, rather than using the mean squared error or some variant of that, because we're now dealing with a probabilistic system, we use the CRPS, which is often used in meteorology as an evaluation metric, which is essentially, in this formulation, just an extension of the mean absolute error, and then this, what we call, well, what we can denote as almost an ensemble variation term. So rather than predicting, when we're training, predicting a single output, we predict an ensemble. We want each of those ensemble members to be close to that single truth trajectory that we consider. And then we want each of those ensembles to be different in some way, or we're trying to enforce a difference there. And then we have this min-max game where we're trying to minimize our distance to the truth, but maximize the variation within the ensemble. And we choose to model the stochastic noise this way, because the self-attention module in the transformer is quite nice in that we now have a sort of state-dependent weighting on how important that noise vector is. And we can kind of think this in a kind of dynamical systems approach. So if we have some sort of manifold here, if we're wandering in a kind of stable configuration here, we might be in this part of the attractor where the noise vector isn't actually going to push us out into a different part of our dynamics. But if we're in a part of our system here where we're about to approach some sort of transition, that noise vector might be able to push us out the way, out of the basin. And the transformer, through training, will learn how to attend to that noise based on the history that it's given. So we have an ensemble here of latitude time plots generated by numerical integration. And then these are the results from our neural network. And we can see that they're reasonably plausible. We see the dynamics that we expect. All of them have this merging event that we see coming up very shortly after the initial conditions. We see a nucleating event and merging events. But excitingly is that it's so much quicker. So even though we're using a very simple system, to generate each of the plots on the top took 180 minutes using a numerical integration and pseudospectral method. The deep learning method took about 5 milliseconds, so it's super quick. Then we want to see if it's stable over long time periods. So the top is a numerical integration over a very, very long time period, and this is an autoregressive method. So we take the output, put it back into the input, and then it gives us the next output. And then this is our model, and we see also that the kinetic energy remains stable throughout the long evolution. And then quickly, because I'm running out of time, we could just compare it to other methods, and these kind of fail for two reasons. So we have a VAE here, where the kind of blurring in the VAE means that we fall into these unstable parts of our dynamics. And then even when we try to use an adversarial part of there, we get this weird mode collapse, where we see that these dynamics get repeated. So it's tricking the discriminator, but it's not actually learning any physics. And we have a few other evaluation metrics, but I don't have too much time to go into those. If anyone's interested, please ask me.